In this video, I want to help you to understand what a p-value is when we do research. Now, I'm going to use the Wolfram language inside of Mathematica to show you what it's all about. So don't be worried about the fact that I'm using a computer language here. It is not about the computer language. I'm just using it instead of using PowerPoint. So no PowerPoint slides. I'm going to show you some code. It's not about the code. I'm not trying to teach you how to write the computer code. It is only used instead of PowerPoint, for instance, so that I can show you what a p-value is all about. Now, I've chosen Mathematica and the Wolfram language, though, because it is a fantastic language to do your statistical analysis in, and then also to demonstrate the meaning behind things, how things work. So I'm not going to show you, it's not about showing you equations of the p-value. I want you to understand what a p-value is so that when you do your own research, when you read a paper, you can understand what a p-value is and specifically, what its uses are and what its shortcomings are. I'm going to start off by doing something completely different though. I want us to go back to school and remember what the equations are for the areas of a shape. Because believe it or not, that is what a p-value is. So let's just start with that. Now, I'm here inside Mathematica, and I'm going to show you just a few of the reasons why I always choose Mathematica above, say, Python or Julia. There is so much built into Mathematica. There's knowledge built into the language. It's a fantastic computer language. One of the reasons why I absolutely love it is instead of writing code, I can write a normal English sentence. I can click here and say I want a Wolfram alpha query, and I'm simply going to type in area of a square. So I did nothing special. I didn't write any code, nothing like that. I hit enter and it's going to query the Wolfram alpha database and give me all this beautiful knowledge about the area of a square. And that's just me asking a plain simple question. So there we have a square. Remember, the two sides are equal to each other. And if I have a side A and the other side A, the area of this square is just a squared. You remember that from school. That's not a problem. Now, it gives you all sorts of other information about the areas of squares. Look at that. It's all fantastic, beautiful. I want you just to think about the area of a square, though. Let's forget the computer language for a minute, although I do love it. So let's look at the area of a triangle. Can you remember that? There you go. You can see how to calculate the area of a triangle. And you see if the sides are A, B, and C, exactly how to do that. And again, all sorts of extra information. Let's go on to something that's a bit more difficult. Can you remember the area of a circle? And there we go. If the radius is A, the area of a circle is pi a squared, or pi radius squared, pi r squared. Oh, let's do one more, the area of an ellipse. Now, believe it or not, we're working our way to understanding the p-value. So here we have our major axis, our smaller axis here, and we see that if that is x and y, or a and b at least, the area is then pi times a times b. Simple enough. All sorts of extra information. Let's try one. Let's try one more. Wolfram alpha query. I'm going to say, what is the area of a trapezoid? Ooh, let's see if it can do that. And there you go. If those are the areas of the trapezoid, there is your equation for the area of a trapezoid. All sorts of extra information once again. Let's bring it back to a p-value though. Believe it or not, the most important shape that we are going to deal with here is the area of a rectangle. Now that's quite simple. Let's see what it is. And there you go. If we have sides A and B, the area of a rectangle is just A times B. Very, very simple. Let's move down through all the information we can get from the language. And now knowing that we are talking about the area of a shape, let me build your intuition for what a p-value is. And we're going to start off by just taking a simple die, that thing that has 6 sides, and you roll it and one of the sides land up, face up. So it has sides with values 1 to 6. I think most people know a die. These are discrete values though. Discrete meaning I can only roll a 1, a 2, a 3, and a 4. I can't roll a 5.5. with a single die. That doesn't exist. So these are discrete values. And I'm going to take that die and I'm going to roll it 1,000 times. I'm going to simulate that with a very easy piece of code. As I said, remember, this is not about the code, but this is this little line that you see here. That's how easy it is. I'm doing this experiment, rolling a die 10,000 times, and I'm saving it as a computer variable. Don't worry about that. The next line of code is what it's all about. Let's execute that. And that's called a bar chart. So you see at the bottom here, 1, 2, 3, 4, 5, 6. So that is what I rolled. And if I just hover over there, you can see how many times, and this is completely random. Well, it's actually called pseudo-random, but that's a different story. I rolled it at random 10,000 times, and it seems I got 1,586 times it landed on 1, 1,660 times it landed on 2, 1,708 times it landed on 3. What you can notice though is that it's, this was random, so it's almost exactly the same. One more thing I want you to notice is if I added up all these values, well, it had to add up to 10,000 because I rolled it 10,000 times. But let's just express this bar chart as something else, something that looks slightly similar, but actually means something different. It's called a histogram. Now you see this histogram, same sort of thing. I see 1, 2, 3, 4, 5, 6 at the bottom, but instead of the how many times it was, how many times it occurred when I rolled my die, it says what was the probability of landing on a 3, on a 4, on a 5, on a 6. Now let's go back up to 1. You see it was 1,586, and lo and behold, well, let's choose this one. There we go. 1,660 times it 2 occurred, and if I go down, I see the probability was 0.166. Well, that's almost similar. Or it seems all I did was I took how many times it occurred, the 1,660, and I divided it by 10,000, because that is the probability of it having landed on 2. And remember the area of a rectangle? That is just the base times the height. We looked at that. That was just A times B. Now these are discrete values. Remember, I can't roll a 5.5. So the base there of the 2, what we are saying to ourselves when we are talking about, just go with me here a little bit, that we are saying that the base is equal to a length of 1. It is discrete. Now even if it was something that was smaller than 1, it being discrete means we take it as a unit length, just 1. And the height is 0.166 of my probability histogram here. And 0.166 times 1 equals 0.166. And that is the probability, the p-value. I can ask you, if I rolled it 10,000 times, what was the probability of getting a 2? Well, it was 0.166, and that was the p-value. It's the probability of something having happened, having done your experiment. You notice there, it is simply geometric area. That is just a p-value. It is just a geometric area, as simple as that. Now let's ramp things up a bit, or at least let's just do something that is not random. There's actually an equation for what is happening here, and it's called a probability density equation or probability density function. It will tell us very nicely what each of these p-values should be. Now remember, this was done at random, and everything being equal, all of these should have been exactly the same, and there's an equation for that. And it is this equation that we see here, the probability density function. It says the probability x of hitting anything between a minimum and a maximum, so that's A and B. The minimum that you could roll was a 1, the maximum that you can roll was this B, which was a 6. So the probability of hitting anything between these, so a 1, a 2, a 3, or 5, a 4, 5, or 6, was 1 divided by 1 minus A plus B. So let's just do that. So it's 1 over 1 minus 1 plus 6. And that is just 1 over 6, and I can ask Mathematica to express that for me in approximate form, so that's 0.166. So the p-value for each of these theoretically should be 0.166, because there's equal likelihood if there's nothing wrong with my die or the way I roll it or the floor it lands on, the table it lands on, that should be the probability. What I want you to see here though is I can create a mathematical equation called a probability density function that allows me not to have to draw this, but to just work out what the probability would be. And that is we're going to build on that, and that eventually is the equation from which we get a p-value after doing a normal medical or other kind of study. Notice that I can develop a function that can represent the solution for me. Now, let's do something else. I've still got my die, and now I get another one out. Now I've got a pair of dice. Now we can call it dice. I like saying the word dice as opposed to a die. That just sounds so weird. Anyway, so I've got my pair of die, or pair of my dice, and I'm going to roll them both. I've got two of them, and I'm going to roll them 10,000 times. Now, I can't do that, but I can ask Mathematica to do that for me, and I've saved it in this variable called dice, and I can say, let's look at what was the first 10 rolls. And you see, this is called a list of lists. I rolled a 3 and a 2, next picked it up, rolled a 5 and a 1, picked it up, rolled a 4 and a 3, picked it up, rolled a 4 and a 1, picked it up, rolled a 6 and a 1, picked it up, rolled a 1 and a 6, rolled it up, picked it up, rolled a 6 and a 5. That's my first 10 rolls. Now let's do something. Let's just add each of these. So it'll be 3 and 2 is 5, 5 and 1 is 6, 4 and 3 is 7, 4 and 1 is 5, etc. So I'm just going to total up each of those rolls. Now, how many? So, I mean, I could roll a 1 and a 1, that's 2, and I can roll a 6 and a 6, that's 12. So it goes from a minimum of 2 to a maximum of 12. Now, which one from 2 to 12 do you think occurs most commonly? I think naturally you would reason to yourself, well, you've rolled a pair of dice before. You know that 2 1s or 2 6s at least is very rare to hit 2 6s. Much more common to do the others. So is there some pattern here? Now remember, all I did was I rolled 2 things that have equal likelihood of any of the sides, landing face up. So, what is going to develop here? So let's have a quick look. Let's tally all of these. And it says I rolled 277 2s, 588 3s, so a bit more, even more 4s, even more 5s, even more 6s, even more 7s, but when it gets to 8, I start going down again. And 9 less still, 10 less still, 11 less still, and 12, even less. So let's do a little bar chart of that and see what happens. There we go, there's our bar chart, and look at that. Is that not one of the most beautiful? Well, this is discrete, it's not continuous values. Again, I can't roll a 7.5, these are discrete, but isn't that the most beautiful bell-shaped curve you've ever seen? So I take 2 things, and each of them has equal likelihood of occurring, but if I do something to them, in this instance we add the 2 values up, I get this distribution that is beautifully normally distributed. It's bell-shaped. And once again, I can express this as a probability. There we go. It was 1,687. And the probability of rolling a 7 was 0.1687. Just how many times I rolled, there was 10,000. And I take how many occurred, 1,687 divided by 10,000. That gives me the p-value. But notice also, I can ask you, what was the probability of rolling a 12? Well, it was less than 3%. It was 2.85%, a p-value of 0.02. So notice how the sum of all of these add up to 1. So you can't have something occur like a 13, or a 1. So it's got to sum, all these probabilities have got to sum to a 1, just as the occurrence of all of these have to sum to 10,000. The probabilities have to sum to 1. And I could also say, what was the probability of throwing something that was 10 or more? Well, I would just add these 3. I would add 0.08, 0.05 there, and 0.285. I could add all of them. So I can color in these 3 at the end, and I can say, well, I can draw a line down here, and my probability of a 10 or more would just be the addition of these 3. So again, dealing with discrete values, very easy to calculate a p-value. It is nothing other than geometric area of rectangles. Again, discrete. So even though it works out nicely that these are, the difference between 10 and 11 is just 1. But because it's discrete, we always take a value of 1 as being the base. So the base times the height here. The height here we can see there clearly, the height of of this little one, for instance, is 0.0285 times 1 equals 0.0285. And that's the probability. It's the geometric area of a rectangle, as simple as that. Now, let's have a look at something that's more continuous, not the step size discrete value with a base of 1. Because we've seen a bell-shaped curve, so it's definitely not stepwise, it's a smooth curve. So what do we do there? I tell you now, it's not a problem. Let's have a quick look. Just as I had my equation there for the probability density function of rolling a discrete uniform distribution, that is 1, 2, 3, 4, 5, 6, and each of them has a uniform or equal likelihood of being, landing face up. I can make a probability density, not me, well, someone very clever, a while ago came up with this equation, and that's the equation for a normal distribution with a mean there of mu and a standard deviation of sigma. And that's what the equation looks like. One of the most beautiful equations you'll ever see. And I want to give you some intuition of how this thing looks and works. So there we go. I can manipulate how much the mean is, so I can move the mean around. First of all, look how beautiful. That's a beautiful normal distribution and beautiful bell-shaped curve. And the area, believe it or not, underneath this line, which goes from all the way to negative infinity, all the way to positive infinity, the area of this probability density function, the area under this curve, and to really do that, we need integral calculus, not just the area of a rectangle that was simple base times height. Here's something different. We need integral calculus. I'm not going to show you the integral calculus. I want you to appreciate the fact that the area under this curve is also equal to 1. And I can also get a little piece here in the corner or wherever, and I can calculate what the area under the curve is. Let's just increase the standard deviation a bit, and you see how it gets flatter, but it gets fatter on the sides. The tails move out and they get thicker on the side. And you can see what the influences of changing, well, the influence of the mean is easy to see, it just goes left and right. And then the influence of the standard deviation on the bell-shaped curve there. If this was exactly 1 and this was exactly 0, we would call that the standard normal distribution. Anyway, so I just want you to appreciate the fact that we can go from discrete values to continuous values. And most of the time that is what we are going to look at. I'm going to move away a little bit from what a p-value is, because I'm quite interested just to show you a couple of other distributions. This is the t-distributions, students' t-test. It's also bell-shaped, but it's slightly different, and it works not on a mean and standard deviation, but it works on something called degrees of freedom. So here we have degrees of freedom of 2 and degrees of freedom of 3. And you see the 2 there, you see how the tails get a bit fatter there, or it gets a bit thinner and it gets pushed up. But that's the distribution you usually use in a t-distribution. Not to worry, let me just show you the chi-squared distribution. Chi-squared distribution also works on something called degrees of freedom, and here we see one with 2, 6, and 20, and you see a chi-squared distribution with a degrees of freedom of 20 almost has a bell-shaped curve, but when it gets very small, like a 6-year or the 2-year, it's certainly not bell-shaped. Okay, so now let's create a population, and instead of there's been 7 billion people, we imagine we're in a town or some area that services some institution, whatever. There's 20,000 people, and imagine there's some blood test. Call that the value for that blood test is called the variable. Remember, variables. And let's just assume that this value that this blood test can take, so if I were to take all those 20,000 people and I were to do this blood test on them, there's an equal likelihood of all of the different values that are possible being available. So it's again a uniform distribution in the population. But this blood test has a minimum value, so the patient that has the lowest value is a 50, and the patient that has the highest value has a value of 110. I just chose that. Now, really it means if we selected 2 groups at random from this population, so the 20,000 that stood in front of me, and I take 30 and I take another 30, there shouldn't really be a difference between the 2 means. So if I take this 30 and I calculate the mean, and I take another 30 and I calculate the mean, and I compare the means, I mean, there was this equal distribution across the possible values. So there shouldn't be a difference, should there? Let's see. So here's my population. I'm suggesting, what I'm saying to the computer is take values between 50 and 110 and give me 20,000 of them, but every value has an equal likelihood of being chosen. Let's have a look at the histogram of that. And here you see the fact that it is uniform. So all the values, don't worry about this one over 110 here. It's just what happens when these graphs are generated. What I want you to appreciate the fact is that if I make a little bundle now, what has changed here and what makes this the fact that these are not, it's not 1 at the bottom anymore, is that there could be a value of 50.1, 50.2, 50.435, 67.876, and what we're doing here is we're just binning them. We're saying, well, let's go from 50 to 55 exactly, and we see how many people were in 50, had a blood value of between 50 and 55, and we divide that by the 20,000, which gives us a probability to fall in that range. I cannot ask the question any longer, what was the probability of someone having exactly 50? Because they could be 50.01, 50.0001, 50.000001 could have been the blood test. These are now continuous values. And I have to bin them now. I have to say between 50 and 55 exactly how many people were in there, divided by the 20,000 still gives me the probability. But look at this. There's an equal probability of landing in any of these little intervals. I want you to appreciate that. Now, once again, I could. There's a little equation just to say what the mean is. And remember, if we look at 110 to 50, halfway between those two is 80. So theoretically, it should be 80. And if I do the theoretical calculation here, you can see that it is 80. But for the 20,000 that came at random, it was about 80.2044. And you see again there, the many decimal values. So we're not talking discrete values anymore. We've moved away from that. But there's an equation just to look at what the theoretical mean should have been and what our actual mean is. Now, so bear with me. I mean, this is crucial, that there's equal likelihood of any of these little intervals, of a patient falling in any of these little intervals. It's not that one occurs more commonly than the other. Now what I want to do is something similar to rolling the pair of dice. I'm going to do a very simplified study. I'm going to take 2 people at random from the 20,000, and I'm going to look at what each of their blood value is, and I'm just going to, instead of adding them, I'm going to look at what the average is. So one had a blood value of 50.8 and the other one had a blood value of 104.786. I add them together, I divide them by 2, and I see, what was the average. And I take my 2 people and I calculate that average and I write it down. And and I throw those 2 people back in the bunch of 20,000. Now I select 2 again. It might be that I pick the same 2, or one of the 2 is the same, but there's 20,000 probability is I'm going to pick 2 other people, and I just do this 25 times over. And every one of those 25 times, I calculate the average of the 2 that I took. And now let's have a look at what happens to the distribution of these averages. I mean, intuitively, you should think, well, it should just be flat, like this curve is flat, because everything is equally likely. So if I were to take 2 of them and took their average, all the averages should be equally likely. Hang on a minute. Let's do that. Whoa! What has happened here? We can see a pattern developing here. It's almost like a little bell-shaped curve wants to come out here. Now, appreciate this. It was equally likely for anything, they're all equal likelihood, and I just at very random chose 2 and did the average. But lo and behold, it seems as if some averages are more common than others. Let me prove this to you. This is called the central limit theorem. Now what I'm going to do is I'm going to take 30 patients and record the average. And I'm going to throw them back, take another 30, and I'm going to do that 500 times, and each time I'm going to record. I create an empty list there, and every time I run through it, I'm going to run do 500 times. So I'm going to go 500 times, choose 30, calculate the average, spit it out. Let's have a look at that. There we go. So definitely some averages were more likely to occur than others. And this is what happens when you do research. You're not going to do it 500 times over. You are only going to do it once. You don't have the time and money to do a study 500 times over. And that one time that you did it, your study, you got a value. Some values should occur more commonly than others. Some should occur rather rarely. And that is our p-value. What was the probability of finding that one that you did? And look at this. This is based on the fact that there wasn't this skewed distribution of this value in our population to start off with. It was very equal. It was very equal. So I didn't do anything behind the scenes to cheat the system and force the fact that I'm going to get these. People were equally distributed here, and still I get this bell-shaped curve out. Now again, I can use that beautiful equation I showed you up above, and I'm going to calculate the mean, and not the standard deviation, but what we have to use is the standard error. And let's just look at this distribution here, which I've grouped people into little bins, so little intervals there. Let's do it smoothly so I can just show you what the theoretical distribution looks like. And there we go, beautiful, beautiful bell distribution. And you could do your study that 30 that you picked landed there, and so say landed here. If I hope you can see my cursor, I can now ask the question, what was the probability of the group that I got, their average being this value or higher? That will be the area. I can draw a straight line down and a line towards this side, and this little funny shaped area, I mean, it's like a triangle, but there's a curve to the one side, so I can't use the equation for the area of a triangle. I've got to use integral calculus, and it can calculate this area under the curve, and I could say, well, the probability of having found a mean of my 30 patients of so much was of so much and more. Remember, this is not discrete. I cannot ask the question, what was the probability of getting an average of 80.5? I can say 80.5 or higher, or 80.5 and lower. And that means I draw a line up at 85 here, and I check what was the area under the curve to the left, or the area under the curve to the right. But it's the same principle as those rolling of the two die. It's just area under the curve. Now let's just go one final step here, and relate it to something that you would actually do. So you would take two groups of 30 people, and you would compare the means one against the other. So I would take two people, 30 values on one side, 30 values on the other side. I get a mean on this side, I get a mean on that side. I subtract the means from each other. And now I want to see, is there a difference in the means? And this is what I've done in this line of code. So I've done that, and lo and behold, I still get this nice distribution, but now it's around 0. 0 is more around the 0 area. I can't ask exactly 0, remember. Around 0, the difference of 0 in the means between the groups should occur more commonly. So if it comes out here towards this side, I can ask 5, 6, 7, 8, 9. So what is the probability of getting a difference in means between my two randomly selected groups of 30 people? What is it to get a difference in means of, say, 9 or more? Well, I would just add these. But once again, we won't do it in this blocky form. We can use the actual equations, theoretical equations that we have for that. And there's our beautiful curve. Now it's not going to be exactly around 0, because this comes directly from my running my experiment 500 times. But I think you can appreciate what is going on here. That given that there should be no difference, given that some deity knows that there is no difference, I can construct an equation which will give me this beautiful shaped curve, and I run my study once and I find a value, and that means I can ask the question, what was the chances of finding my value or more than my value, the difference in my means, or more than, or less than, or different than, doesn't matter, all these questions. But in the end, I draw a little line, my value, my one study falls somewhere down here, and I can get an area under the curve towards one of the sides. Let me show you that in these two little graphs that I've drawn here in a different program, and I just imported it here. So imagine then you do your study, and you take 30 people in each group, and one group got a certain drug and the other one not, and you measured something, and you want to see is there a difference now in the means between these two values. And what you would do now, remember, you can't do this 10,000 times over. You can only do this once. But what those equations will do is they'll take the one that you got, and it'll draw this theoretical nice little curve with a total area of 1 underneath. You will then do the following. You will say, I want a p-value of 0.05, and the equation will actually work out for you. Well, if I draw a line right here, this orange one, and everything out towards that, this area is behind the black, so imagine the black wasn't there, so all the area of the orange there, that is 0.05 of the area under the curve. It will work that out for you. Now you'll take your specific results, and there's a little equation that you do to mark out where you will then put your dot here on the x-axis, and it will fall there. And it'll work out for you what this area under the curve for the black is, which is obviously here less than 0.05. So the probability of you having found this specific result, given all the possible ones that could occur, theoretically, your p-value was less than 0.05. Now this is called a one-tailed hypothesis. Most commonly in research, though, we'll have what is called a two-tailed hypothesis, where we say, we think our null hypothesis is there's no difference between the groups. Our alternate hypothesis is there is a difference. So if I subtract the mean of the one group from the other, the one might be more or less than the other one. I'm not saying specifically beforehand that I know, and that is really the way you should do most research. When you have a one-tailed where you say, I definitely know the second group should be more, and you have a one-tailed hypothesis, you must be able to logically explain to your colleagues who's reading your research and convince them through logical arguments that you should have chosen the one-tail. So it's much more common to do this two-tail. So the two-tail says the null hypothesis is there should be no difference. And I think I've shown you now the way that these things are constructed is the fact that there was no difference. There was an equal distribution of a uniform distribution of these values. It wasn't like there was one lot, more people had 80 than 50. That was equally likely to have everything. So the p-value comes from the fact that in reality, there is no difference between the two groups. Given that fact, you now construct this nice little graph that I've shown you, and some differences will be more common than others, and you just find one of the uncommon ones, then you have a small p-value. That did never ever did this prove that the one group was different from the other. You never prove that. There is no equation that can prove that. This is built from the fact that there should be no difference. Statistics like this is built from the fact that there should be no difference. In reality then, given there is no difference, some deity knows there's no difference, you just found one that a result that would less likely to be found given that there is no difference. And then we decide, okay, we'll reject the null hypothesis and accept the alternate hypothesis, and we'll say there is a difference between the groups. But that's just something we decided. We never proved this. This inferential statistics cannot prove this. It is based on the fact that underlying those patients that you took, there really is no difference. You then find a difference that should be rare to find, and we call that, there is a difference between them. Well, I think you understand now. Now you have a deep intuition about what a p-value really is. It is a geometric area based on the fact that on equations that were developed for there to be no difference whatsoever. It is just the fact that we as humans have decided that if we get one of these differences that is less likely to have occurred, then we'll call it significant. And we had this cutoff of 0.05. So just to get back to this, so what we do is we don't know if the one is going to be more than the other. We actually draw these two orange lines with slightly further out, and we have 0.025 or 2.5% on the one side and 2.5% on the other side, and whatever of these two black values we find, we just duplicate it on the other side and we just add the two black areas to each other. So it'll always be double what it is. So your p-value, if there's one way to cheat, just go from a two-tailed to a one-tailed, because you just divide your p-value in two and suddenly it'll be much smaller. Of course, it'll be half. And you can cheat that way, which you should never ever do, and that's a horrible. So when you read a paper, see what kind of hypothesis people chose, one-tailed or two-tailed alternate hypothesis, and if they chose, or if they don't say, treat that with some suspicion. And if they do say, and it was one-tailed, they better convince you why the one-tailed should have been chosen. So we do this two-tailed thing. Because I love Mathematica, let me just show you. So I'm just going to create 30 people, two groups, 30 people, and from a normal distribution, I'm going to choose a value with a mean of 100 and a standard deviation of 10, and the other 105, 115. Let me just show you at random what happened here. So the mean of my first group was 99.867. The mean of my second group was 103. I can ask, let's just look at a box and whisker plot. You know what those look like. And I can ask, is there a statistically significant difference between these two groups? Couple of functions you can use in Mathematica. The one is called the location test. Do it there, and I see there's my t-statistic. That is the little black line. That's where you draw your little black line there. It takes your values and converts it into a point that you put on the x-axis. You then reflect it on the other side with a positive as well, and it works out the p-value for you, 0.31. So given only this information, it uses those beautiful equations that we saw before, draws that nice little bell-shaped curve, and it says, well, the difference between these two was minus 4, something around there. And that means on that x-axis, that will fall on negative 1.01935. So that's so many standard errors away from 0. Don't worry about that. Duplicate it on the other side, work out the area under the curve, and lo and behold, it says, look, buddy, this area under the curve was not so uncommon to have occurred. The difference in the means were not so uncommon given all the possible ones that could occur. And let me just show you, there's another way, just right there, t-test, and let's say group A and group B. Very easy in Mathematica to get these p-values. Very easy to do. So I hope this has given you some intuition about the p-value, what it really means. It's just this geometric area based on the fact that there isn't any difference. And we are weird as humans. We just decided that 0.05 is going to be this cutoff, and then we think there is a difference. You've never proved it. You never, ever proved it. This is just the way we constructed statistics. Clever people constructed statistics, and I think we abuse it. So you can really start to get this uneasy feeling about a p-value, and why some journals are moving away from it, and how easy it is to cheat with a p-value, and how little it really means. And there's some, there are other things that we should look at when we do. But you're going to see a lot of p-values, and you should know what it's all about.